State Kirchhoff's second law. The sum of EMF, electric motive force, and circuit is equal to the sum of potential difference for the component, but this is just in one loop. A battery of electric motive force EMF 9 volt and negligible internal resistance is connected in series with variable resistor X and thermistor Y. Figure 5.2 shows the relationship between temperature and resistance for the thermistor and resistor. The current in the circuit is 1.1 times 10 power negative 2 ampere. The potential difference across Y is 4 volt. Calculate the resistance of X. E equals Vx minus Vy. So Vx, potential difference of X, equals E minus Vy. 9 minus 4 equals 5 volts. Now we'll go to find Rx equals Vx over I. Vx, as we found, 5, and the current, total current, is 1.1 times 10 power negative 2, gives you resistance about 454.5 ohm. Final answer 450 ohm. The temperature of Y is changed to 190. The resistance of X remains unchanged. Determine the new potential difference across Y. Let's project the graph for 190. A line here, it intersects with the curves 0 and 50. It's almost in the middle, or actually 25 degrees. When the temperature equals 190 degrees, the resistance of Y equals 25 ohm. We will apply the equation of the potentiometer. Vy equals Ry over the sum of them, Rx plus Ry, times Vn, or EMF, equals Ry here, as we calculated, 25, Rx we calculated here 450, no change, and Ry 25 times the Vn, which is 9, equals 0.47 volt. The answer 0.47 volt. The resistance of X is increased. The temperature of Y remains at 190 degrees. By reference to the current, so we should mention the current. By reference to the current in the circuit, state and explain the effect of this change, if any, on the potential difference across Y. So, the resistance of X increases. So it makes the total resistance also increases. What's the effect of this on the current? The current, total current, decreases. Also decreases. Question 6. Light of a single frequency is inserted normally on a diffraction grating. An interference pattern of bright and dark fringes forms on a semicircular screen shown in figure 6.1. It has a wavelength of 500 to 20 nanometer. The separation of the lines in the grating is 3.8 times 10 power negative 6. Determine the total number of bright fringes formed on the screen. We don't know how many orders, so we'll assume that the higher order at an angle of 90. Of course, will be less than 90, but we'll assume that is at angle of 90. So we'll assume the angle, the higher order at angle of 90. Subject, so n equal d sine theta over lambda. It's 3.8 8 times 10 power negative 6. The angle, as we said, 90 sine 90, which equals 1, of course, divided by lambda 520 times 10 power negative 9 gives you 7.5. Number of orders should be a whole number. So not reach 8, of course, 8 orders. So the maximum number or the higher order is 7. But he asks here not for the higher order, he asks about total number of fringes. So we have 7 fringes upper and the same of them down plus n equals 1 or 0 order. So the sum of them, number of fringes that we see on the semicircular screen, equals 7 upper and 1 0 order plus 7 another 7 which equals 15. So the final answer 15. The light is replaced with a red light of a single frequency. State whether the frequency of red light greater than, less than, or the same. We know that for the red light it has longer wavelengths and smaller frequency. So whatever the light, the frequency of red light is less than this light. State and explain the effect of the change number on the number of bright fringes formed on the screen. A calculation is not required. That if we write the equation, n equals d sine theta over lambda, so we see here n and lambda are inversely proportional. So when the wavelength increases, which means the number of fringes decreases. A particle Q and particle R are each composed of one quark and one anti-quark. State the name of class or group of particles that includes Q and R. The class of particles that made up of quarks are hadrons, but the group of hadrons made up of quark and antiquark, meson. B. Q has a charge of -1, whereas the elementary charge R has a charge of 0. Complete table 7.1 to show a possible second quark in each Q and R. For the particle Q, the charge is -1. One of the quarks is strange. We need another quark, which is anti-quark, to complete charge to become -1. The charge of strange, if we check the table of the quarks, charge of strange is complete this charge -1/3 with a charge from anti-matter to become the -1. So we need -2/3. We find -2/3 here in up and charge and anti-top. So the charge of the second quark, we can choose any one, up, anti-up, anti-charge, anti-top, any one of them. We choose anti-up. For the particle R, charge is 0. One of them is anti-up. What's the charge of anti-up? And -2/3. So to complete to reach 0, so we need +2/3 from matter, not antimatter. In the matter here, we have +2/3 in up and in charge and in top. Choose any one of them. We can choose charge.